Hello everyone. In this video, we will talk about improved analytical LDD MOSFET model for digital and analog circuit simulation for all channel length down to deep submicron. I am KUTHUBBU RABBANI SYED. My team members are JEYAPRAKASH and ARASU. We are from Department of Electronics and Communication Engineering at Tyagaraja College of Engineering, Madurai. First of all, what is LDD? LDD means lightly doped drain. It addresses the challenges arising in the miniaturization of MOSFET used in integrated circuit. As semiconductor technology advances and devices are scaled down to deep submicron dimensions below zero point 0.1 micron, traditional MOSFET models face limitation in accurately predicting device behavior due to various physical effects becoming more pronounced. These effects include short channel effects, velocity saturation, and quantum mechanical phenomena. The goal of this improved analytical model is to provide a more accurate representation of the MOSFET behavior at deep submicron channel length, enabling reliable digital and analog circuit simulation in advanced semiconductor technologies. Key aspects of the models are inclusion of short channel effects. Short channel effects such as drain-induced barrier lowering and subthreshold slope degradation are considered to accurately capture their impact on device behavior. Then velocity saturation and mobility levels. For velocity saturation, at high electric fields, appropriate velocity saturation models are incorporated. Additionally, mobility models are adapted to accurately represent the electron and hole mobility at deep submicron scale. Quantum mechanical effects. At deep submicron channel length, quantum effects like quantum tunneling and quantum capacitance becomes more significant. The model should incorporate suitable quantum models to address this phenomena. Then parasitic capacitance and resistance. It can influence circuit performance. It should be included in the model to achieve more accurate simulation. The model should account for temperature variation and process induced parameter fluctuation to ensure robustness in different operating conditions. Then key points regarding the LDD effects in MOSFET devices. The purpose of LDD. Its purpose is to reduce the high lateral fields at the drain side in scaled down MOSFET devices. The bias dependent effects are specifically on electrical channel length, series resistance, and overlap capacitance. Gate voltage dependent series, as the source series resistance is divided into intrinsic and extrinsic parts. In extrinsic resistance, it depends on the actual layout. It becomes gate voltage dependent due to the modulation by the gate bias. As the simulation of series resistance is measured and simulated using the transition function, the resulting function is become complex, so the series resistance is introduced as an external voltage dependent resistance. The LDD effects in MOSFET device including bias dependent electrical channel length, series resistance play a crucial role, especially in submicron technologies. Types of LDD MOSFET. Standard, retrograde, asymmetric, dual material.
Hello friends, myself Tamlarsu from Department of ECA at Tyagaraja College of Engineering. I am here to describe the parameters used to model the drain current in deep submicron MOSFET devices. Surface potential pi s and bulk charge factor beta. The surface potential pi s on the onset of strong inversion is given by the equation pi s equal to 2 psi f plus np hit star pi t. Here, psi f is the bulk potential. Nfit is a parameter considering the thickness of inversion layer, which lies between 7 depending on the process, and pi t is the thermal voltage. K star T by Q, where K is the Boltzmann constant, T is the temperature, and Q is the charge of the electron. The bulk charge factor beta is used to model the drain current and is given by beta equal to 1 by 1.744 plus 0.836 star pi s minus VBS, where VBS is the break gate voltage. Effective gate to source voltage VG self and effective drain to source voltage VD self. To describe both the drift and diffusion components of the drain current without discontinuities in the derivatives, two transition functions are introduced. Vg sub equal to log Z star VDS plus Z star VDST. Vd sub equal to log Z star VDS plus Z star VDST, where Z is equal to e power m and m is a parameter that controls the soft transition between the triode and saturation region. Threshold voltage. The threshold voltage is defined as VTS equal to VFP plus AM star square root of 2 star NSS star pi s minus VBS star sin minus TPG minus 7 minus QJ, where VFP is the flat backgate voltage and AM is the work function. NSS is the parameter related to the surface state density. TPG defines the type of polygate material. For example, plus 1 for N channel, minus 1 for P channel MOSFET transistors. QJ is a charge in gate oxide. Short and narrow channel effects. The function Fc models the short and narrow channel effects and is given by Fc equal to 1 minus K1 star L by lambda power Es plus K2 star W by Ws minus K3 star Vds minus K4, where L is the channel length, lambda is a process dependent parameter, W is the channel width, Ws is the reference channel width, K1, K2, K3, K4 are coefficients that model various effects. Es is the component that depends on lateral field combination.
Hello friends, myself K. JEYAPRAKASH from EC department at the ARASU College of Engineering. Now we can see parameter extractions, E parameter extraction process and present the result for an N channel transistors with the channel length 0.5 μ. Next one is the separations of voltage dependence. The voltage dependence of series resistance, effective channel length and mobility reductions are separated to determine the parameter set that is valid from long channel to deep submicron region with good accuracy. Third one is the methods of extraction. The text mentions using a method similar to one described in a reference for the extractions of voltage dependent channel length and series resistance. This method is based on channel resistance measurements. Fourth one is the validations. The effective geometries are verified using capacitance measurements and the model performance is validated by comparing measurements and simulations of test circuits. Examples is the ring oscillators. Next one is the thermal noise. These are the result for an N channel transistor. From the graph x-axis drain current, drain source, and the y-axis is drain current. First one is the ID currents are drain current, and the second graph is the output conductance GDS, and the third graph is the triode regions. There are transitional regions between linear and saturated operations. Fourth graph is the sub-threshold current. These are current in a weak inversion regions. Thank you.